Oh, that's quite an addition. Awesome, though.
Okay, so Fraxl. The general idea is that in all kinds of applications, it is common practice that you need to access a variety of data sources. Um, so there needs to be a good system for managing those different data sources. Um, the naive implementation of managing these data sources is just to do everything in I/O, right? You want to, sorry, you don't want to, but the naive implementation is just to use Monad I/O and Monad Reader for your whatever kind of settings you need to read from for like a connection pool or whatever, and then do your code inside that Monad. But there's obviously tons of downsides to this. So like you have to use I/O in this kind of implementation, which means that like you're prone to unchecked exceptions, or you might do impure code where you really shouldn't be doing impure code. And then of course, like you can see right there, it's leaking that abstraction of the I/O connection pool, whatever that is. Whoever calls this function has to be prepared to offer you this connection pool thing, even if it's not necessarily that call site's concern, right? So if you can, you'd like to abstract that away, and of course there's various ways of doing that, but I think I've got a pretty good one. So obviously, also there's concurrency and caching would be an absolute pain with this, because think about it, like that code. That monadic expression just looks pretty simple and nice, and that's a good thing, right? Being able to say just get all the user IDs and then iterate over them and get each one's username, it's nice and clean, and you don't have to worry about, it's currently not worrying about concurrency or caching or anything, but imagine if it had to, that would be significantly more complicated, trying to actually get all of those iterations to parallelize. And trying to get things to cache in case any of these have already been fetched before. So Haskell is a library that is made by Facebook. It's open source that tries to offer solutions to all these problems. It does caching, concurrency, batching, and it makes for this clean, non-leaky code. So we see the same kind of code example, but that type signature is extremely simplified because you don't have to tell it like, hey, we're working in I/O. You don't have to tell it we need the connection pool object or anything like that. All you have to do is say, I'm working in Haskell, and I want to use the get users and the get username functions, and it's all just going to work out fine. And so Haskell will help you manage to get those to parallelize, and it'll automatically cache them.
Was this automatically parallelized right here?
So the thing about Haskell is that it doesn't just implicitly parallelize everything. It gives you the option to implicitly parallelize everything. So what's happening here is you're using a front end, an interface, over some API, and then somewhere else in the code you have to declare, okay, I'm going to interpret that interface this way. And Haskell gives you the tools to make that parallelizable really easily.
So this expression could be parallelized, depending on the back end?
The back end will determine how this expression behaves in terms of parallelization and everything.
Really?
Yeah. So yeah, like I said, this is just making access to that get users and get username function. Those would be part of a data source. And a data source kind of has three main components to it. There's the interface, which is these functions that let you access the resources you need. There's a monad, which is the actual means with which you perform computations on it. The way that it is actually, the way that results are yielded to you, I should say. And then there's the interpreter, which has the job of actually taking requests and converting them into the results that you need, and actually like going and doing the fetches and all that. So just as a simple example, so let's say we have this UserDB data source, and the purpose of it is that you can either get all the users in the database or you can get the username of a particular user. What's important to note here is that it's not actually, this data type doesn't store the results in any capacity. It merely represents them at the type level. So that getUsers constructor isn't storing any kind of int array. It's just telling Haskell like, hey, when you fetch this, I promise I'll yield an int array or an int list. And then of course getUsername just stores an int and then promises Haskell it will yield a string. And then you can use these are just wrapper functions essentially to make it so that you don't have to manually type data fetch every time. But the data fetch function essentially lifts your interface into the Haskell monad.
Shouldn't Haskell have some reference to UserDB in its type?
I'll get to that. That's a main part of that's the reason that Fraxl exists, is that Haskell doesn't actually do that.
Oh.
Yeah, so the data fetch function will lift your interface into your monad so that you can actually start doing computations with it.
Can I ask, if you don't have to go into this, but you're using a get there, right?
Yeah.
What is that giving you? Like, what's the? I'm still trying to remember my right around get actually. I'm trying to figure out.
Oh, okay, I
I'm
see.
I'm trying to figure out what's
All
the
right.
practical use. All the practical uses I've seen so far have been recursive grammars.
Sure.
I'm so like, okay, well, here's one that's not a recursive grammar.
Yeah. So the point of this is that whenever you have an instance of UserDB, that is meant to represent a request of type either list of int or string. So that is a request of one of those two types. By using a GADT, it restricts those requests so that it can only be one of those two types, right? So I can say I'm either this getUsers request, which has no parameters to it, no stored content, and just always refers to a request of list of int, or it's the getUsername constructor, which refers to which stores an int and then refers to a string. Yeah, so it's not. Let me see. The point of it here is that we don't want UserDB to actually be some kind of functor. We don't want that A type to be anything that the user wants. We want that to explicitly just be whatever the constructor says it needs to be.
Okay, so yeah, I see it now. So the A is not really for the user.
It's for the
It's
constructors.
For the constructors.
Yeah.
I see.
Yeah. Okay. So then, at those bottom line there, the instance data source UserDB thing, that's a little complicated. There's actually a whole class hierarchy there. Like you have to implement, I think, ORD and Hashable and a few other things that are Haskell specific. So that's simplified down to one instance. But the point is that the data source class lets you say, lets you tell Haskell how to actually go from a request to a response in the I/O monad. So in that
UserDB is really just a representation under request.
exactly, it's an interface. Is what I've been calling it.
Okay.
So yeah, in the data source class, you'll define this function called fetch, which takes a list of or an existential list of your requests, among other things, and you're expected to fill those requests with results using the I/O monad. Let's see. So, those of you who are more familiar with monads may have seen that previous example and thought, like, man, how does that parallelize if it's using a monad? Because monads aren't concurrent. When you do that expression there at the top of the screen there, although getUsername 1, 2, and 3 are all irrelevant to one another, and they could easily be parallelized, because we're using a monadic expression, they won't be, because each expression depends on the previous one, right? So Haskell, when you use the monad type class, Haskell doesn't actually have a way to look at how your computations can be parallelized, because it can only see them one at a time, whereas to parallelize them, it has to see multiple at a time. So the solution to that is with the applicative type class, which, if you look at the applicative operator there, its two arguments are both in the applicative context. So unlike monad, where you have to compute the left-hand side in order to use the right-hand side, an applicative allows you to dive into both sides of the operator and analyze them both together. And so Haskell does that by looking at all the requests stored in both sides and then merging them together to have one result which has all of those requests together. And then that way you can look at that group and parallelize them all together. Now technically this breaks the monad laws if you're being in a certain viewpoint, I think. Because technically that operator has to be equal to the monadic app function. But in general, the theory is that as long as they're morally the same thing, it's fine. It doesn't break the laws. So we treat that as non-law breaking in Haskell.
I remember a discussion about that.
Yeah.
Your applicative implementation should match your monad implementation.
Yeah.
That sort of makes it impossible to ever use applicative for parallelization.
Exactly. Edward Commit helped me a lot with that. He helped me a lot learning how to actually make this work in terms of the theory. Let's see. Yeah, so when we see this expression, this for loop, which we want to have all those elements parallelized, if it used monad, it wouldn't. But the for function actually doesn't use monad. It uses applicative, and it results looking something like this, where you have whatever...
Is that more recent change?
I don't remember if for even existed before traversable was a thing, but I know that now it is a part of traversable, and it's essentially just traverse with the arguments flipped, so it uses applicative. Yeah, so using for results in something like this, where you just have all of those things next to each other with the applicative operator in between them. Obviously, that means that if your monad parallelizes with applicative, then those will parallelize, which is good. So the drawbacks with Haskell or with Haskell, God, that's so annoying. The drawbacks with Haskell are that you have to be living in I/O. So if you want to use something else like
STM?
STM would be a good one, although you could theoretically still use STM in Haskell if you just use... theoretically, you can use almost any monad if you make abusive use of the state keys, but that's beside the point. By default, you're using I/O, and there's no clean and clear way to break out of I/O and use something else. And in fact, this is... in some preliminary performance testing that I've done, I found that with Fraxl, if you use identity instead of I/O in something that can use pure code that doesn't need I/O, Fraxl will perform like twice as fast that way. So like when you don't need I/O, which granted is going to be rare with something like this, but if you don't need I/O, you can get pretty dramatic performance improvements by dropping it. So the fact that you can't get rid of I/O with Haskell is kind of a problem. The fact that you can't use some other underlying monad is a problem. Yeah, and then, like I said, there's these state key things in Haskell where one of the superclasses of the data source class is something state key something. And essentially you have to define like my data source has a certain type as its state. And whenever Haskell calls my data source's fetch function, it's going to give me my state, and I can read from this. And really, it's more of a reader than state, but they labeled it state. You can read from your state value and use that to actually do stuff. And the point of that is that from the top level, you can set like configuration options and all sorts of other stuff in your state, and then your data source has access to it that way. But what this also means is that you have to initialize those state keys, which means that if you don't initialize the state keys and then you call a function that uses that state, that uses that data source, you'll get a runtime error. Not a compile time error because there's no type level check on what data source you're using. So you get a runtime error. Yeah, and then of course the state keys are just kind of an ugly solution anyways. It'd make much more sense if you could use an arbitrary underlying monad and have like a monad reader or a monad state underneath of it. And then finally there's no meaningful composition in Haskell. It's sort of just this big black box of monad.
You mean composition with what? Not within itself.
Well, in both directions, really. It isn't made of general components. It is one piece, right? Whereas what we could have is a more general composition of items, which I'll get to in the next slide. But it also doesn't compose the other direction. It isn't a transformer, so you can't put it in the middle of your transformer stack. It has to be at the bottom, which means that you can't be using arbitrary I/O in Haskell. Well, you can, because Haskell does offer a function for lifting I/O, but they recommend against using it. So it forces your base monad to be Haskell, which is a little bit unfortunate.
Which is fine probably for their use because it's completely. That's that one.
To be honest, most of the time it is going to be fine. Almost every situation it probably will be fine, just because like you usually don't need two different base monads, right? So it should be fine, but there's no reason to have that problem.
And what if you don't want caching?
That's the other thing, and I'll also get to that. If you don't want caching, then your only option is to implement the I think order type class incorrectly.
It's terrible.
Yeah, and that would be a solution to break caching. But even then, like it's still doing cache checks and it's still storing some kind of cache. But you otherwise don't really have an option to it. So on composition, if we look inward, we can break Haskell down into a stronger composition of tools. For instance, it's a free monad. So Haskell takes an arbitrary set of data sources and merges them into one monad, right? Which, I mean, because those data sources are arbitrary, by necessity means it's a free monad, even if it isn't like under the hood using a particular free monad or anything like that. Haskell's a free monad. And it uses a collection of data sources as the thing it's a free monad over. And then it requires that those data sources implement certain classes so that they can be cached and also so that they can be batched or parallelized. There's no need for all of this to be coupled together. You can split this into multiple different components and get something that is more configurable, easier to understand on some level. Basically that. So if we look at the free monad, I'm going to give a sort of simplified example or explanation of the free monad. Here we see the free data type just takes any f and becomes a monad that way. Usually free monads that you look at are going to require that f be a functor, but there are free monads that don't require that, and for the purposes of this presentation, f does not need to be a functor, so I'm just going to ignore that part. So given some f, free is a monad over f. So if we look at this in terms of the data sources, if we just plug a data source in for f, then that's making a monad out of an interface. That's 2 out of the 3 boxes, right? Which was that a data source needs an interface, a monad, and an interpreter. So that gets you the monad out of your interface. Then the last thing you need, obviously, is the interpreter, which the free monad is designed to be interpretable. You can use some function to translate your free monad into some other monad, and then you can actually run that and make it useful. So in this case, interpreting would be the fetching function. So if we want to actually use that, we would use something like this. We would have this, and I'm sorry for that being a little low on the screen. We'd have this fetch function, this fetch type that says, given requests of type f, return a monad of type m. And then run free will say, we'll essentially iterate through the structure of the free monad, perform all the requests using your fetch function, and then return that monad. And that for all x there, that's essentially just saying that the fetch function has to be polymorphic. It can't be fixed to a or anything. It has to be able to take any type argument. So x can be anything when you refer that fetch function. Yeah.
You need it to work for all a,
yeah.
all x, so that you can interpret some arbitrary structure.
Exactly. Yeah. So because now in the traditional free monad with a functor in it, you don't actually need that for all x because when you're using the functor, it actually does map everything down to A.
You can just map functor across that, right?
Yeah, and that's the way that the free monad traditionally works, is it maps everything to A, and then that way you can use an interpreter that doesn't have to use this rank n type. But with the kind of free monad that I'm using, you do actually need to have that for all x because the components may be a variety of types existentially. So yeah, with this we still have a problem because the free monad is still just a monad, right? Obviously, because it's a monad, it's an applicative, but because it doesn't do anything to make use of that applicative instance, it has to be a monadic applicative instance, and that just says that the applicative operator is essentially going to equal that monadic app function that I talked about earlier. And
So
as
you're using parallelization, I was saying.
yeah, so as I said before, the app function doesn't actually allow any sort of parallelization that way because it's based on monadic stuff. So using just this, you can't actually get any kind of parallelization out of it. It'll force you to just look at the requests one at a time.
So the interpreter runs. So because you're passing the interpreter in, right? The fetch function that has to run for each, like iteratively over the monad as a build. Is that what you're saying? You can't just hand it the whole structure at the end.
Yeah. So what you'll do is you'll write your program and say like this program is an instance of the free monad over user DB, whatever returns whatever, and then you write your whole program in respect to the free monad, and then whatever program results from that, you'll take that and pass it into this run free function, where one argument is that, and the other argument is a function that will translate all the requests into actual monadic results.
Oh, okay. So one at a time.
Yeah.
Still.
So here, yeah, and you can see that in the type signature of the fetch type. That function can't take multiple requests, right? That function has to take one request at a time, which isn't what we're going for. So we kind of have to cheat. We have to use the free applicative as well. The free applicative is much like the free monad, just an arbitrary applicative over arbitrary type constructor f. So the difference between this and the free monad is that they preserve different structures. The free monad preserves the monadic structure, the free applicative preserves the applicative structure, which means when you interpret the free applicative, you can actually see all of the requests at once. And that's just a property of the free applicative, is that you can see all the requests at once. So trying to get these things to compose, I had to create a different sort of free monad. So we'll call this free prime. Free prime FA is a monad given some applicative f, which is, even stronger than the traditional free monad, because the traditional free monad only requires f be a functor, but here we're requiring it to be an applicative.
I see.
So it's stronger, but that's not what we're looking for. So when we take this and apply it with the free applicative, we get exactly what we were looking for, which is a free monad that will let you examine all of those requests in a applicative expression at one time, because that applicative instance for this particular free monad is optimized to use f's underlying applicative structure.
So is app, capital A app, is that the free app, basically?
Yeah, it's a free applicative. Yep.
Okay.
Yeah.
As
So
opposed to free, the free data type, which is just for monads.
yeah, free represents monad, app represents applicative, and like I said, they just have fundamentally different structures because they're trying to preserve different structures. So with this free monad, free prime, the applicative instance has to have that operator changed so that whenever it encounters two f's, it uses their applicative instance to combine each other. Yeah, and then that way, when you combine the free applicative and this free monad, you get a free monad over arbitrary type f that lets you see all of the requests at once, exactly what we wanted. Now, this does actually incur some problems which I won't get too deep in, but essentially, because we're changing the way that applicative instance works, we end up breaking the applicative operator equals app law, but as long as you use a responsible interpreter, it's fine. It actually works out just fine. So this is just like Haskell. We have to break that law. There's no way to do it without breaking that law. So we just kind of morally follow the law and say this is fine.
Is the law that you just that not only does the result have to be the same, but the effects have to be the same between the two?
No, the law is that to an outside user, the two should not produce different results, right? So
it's possible for you to produce different results this way?
No, because when we actually get into using the interpreter is built such that you can't make it different.
Okay.
But theoretically, it is entirely possible that you can use the applicative operator with some f such that it breaks that law. It's just that as long as you interpret it correctly, you won't break the law. You have to interpret it such that every applicative combination of f's results in an applicative composition of result monads in the same structure. So when I have like something app something app something, I have to have that exact same pattern repeated in the monadic part of it. Which is why it works really well with the free applicative, because we get that structure laid out directly in front of us. So we get that structure, and then we can say, okay, given that structure, let's just go ahead and repeat the exact same structure in the target monad. And then that way we make sure that we're following those laws. Might be a little over the head, but
I get it. We're trying to interpret the law so we can properly interpret.
Yeah, so it just comes down to interpretation. Yeah, so then if we take a look at data sources using this method, so if we look at the get users function, we see one thing right off the bat, which is great. We have a type guarantee. We know that the free monad is over UserDB, and anyone who has to use this has to provide UserDB. So we have a type level guarantee. No more runtime errors with state keys. And then obviously the implementation is really simple. Just like the data fetch with Haskell, this lift free just takes the get user's instruction and lifts it up into the free monad.
And that gives you both the monadic and the applicative.
Yeah, because like I said, when we go back here,
I see. Yeah, it requires it.
Free no prime is just free prime with applicative applied to it, so we know that it is a monad for any type because applicative is an applicative for any type. Yeah, so then we get to the interpreter, which, as I said before, we have this problem where we're still only interpreting one request at a time, and we need to be able to interpret multiple requests at a time. So the easy solution to this is just to do that, where you take the entire applicative structure surrounding f, and then compute an m out of that. Now, theoretically, I think it would be better if it were. Yeah. The way I actually implement it in Fraxl is a little different than that, and the way it's actually implemented more strongly adheres to that interpretation law that I talked about. But this obviously could theoretically break the law pretty easily, but we'll ignore that. So what this is doing is whenever you receive this applicative instance, it lets you see a whole range of requests at a time. Because like I said, the applicative lets you see the entire applicative structure. The free applicative lets you see that whole structure. So you have the entire list of effects of requests that were made, and you can turn all of those into the resulting monadic computation. So here that gives us the parallelization that we needed, right? Which is that's good enough. Now that kind of handles composing inward. Now we have a stronger composition inward. We have the free monad and the free applicative and the data source all combining as a multi-layer system that lets you build such a monad like Haskell. But we still need to go outward. We still need to make a transformer. And luckily, there's a very easy way to make a transformer out of a free monad. I won't really get into the detail here, but yeah, the free monad there's an easy pattern to follow to take a free monad and turn it into a free transformer. So here we have like the free T prime takes a arbitrary applicative F and then underlying monad M and is a monad. Whereas the free T there just does the same trick as before, where we apply the free applicative to that free monad. And this way we have a free monad transformer with applicative optimization, which is ideal. We wanted a transformer and we wanted applicative optimization, and we have it. And what's cool about this is that you can have the underlying monad and the fetch target monad be the same, right? So we can have the run free will take some fetch function which will result in monad M after processing requests of F, and then it will take a free monad over F, over F and over M, and then just produce an M out of it.
So you're fetching and has to run the same base monad as your.
Yeah, which is kind of a good thing because that means that your fetch function can specify arbitrary base monads.
So, for example, if you were an STM, it'd have to be the same STM.
Mm-hmm. Yeah, you could make a fetch function that has STM as the base monad. Yeah, for the most part, what you'll be doing is using MTL style classes and saying like my fetch has type monad state something or other M fetch FMA, right?
Right. That means so you're only running M once right above this, right?
Yeah. So
if you're running STM, the atomically is going to be on the left side of run free, not on the right. It's going to be the whole thing going to run the same atomically block. Is that right? If your base monad was STM,
yep.
That's good.
That's good.
That's really good.
Yeah. So yeah, the fetch function will take all requests out of the free monad and translate them into the target monad, which is the underlying monad, and then that's the result, which is exactly what we're looking for. This allows for more than just the data source, right? Your code now is allowed to do a lot more than just fetch calls. They can also start using state, and they can use whatever other monad you have under your belt. Both your data sources and your code may use more than just the data sources now, more than just I/O. So the data sources are allowed to use arbitrary underlying monads. The code is allowed to use arbitrary underlying monads. And you don't sacrifice the base monad. You don't have to say like the base monad is Haskell now. You can say base monad is I/O, or its identity, or its list, whatever you want. So the base monad isn't sacrificed, and of course it has all the same benefits. It has the free applicative structure to it. It has the free monad over that, and it obviously has the same type safety, where the function within the free monad that depends on a certain data source means anyone calling it has to also depend on that data source. So then the data source requirements. I think I kind of jumped the gun and talked about this already. The interpreters may require arbitrary constraints. So the user DB fetch here is just saying like, I need to be in I/O because I need to actually touch the database, and I need a reader with my DB config, and then I can properly give you a fetch function that will go from requests of user DB into this arbitrary monad. And the nice thing about this is that users of the user DB interface don't have to see those monad constraints, because all they have to care about is that they have a free monad over user DB, and then later on somewhere else can take that and apply this interpreter to it. So the code that actually uses UseDB doesn't have to care about this at all. It doesn't have to care about those constraints. But the fetch is allowed to constrain those. And there's no tie to I/O. Again, this is just freeing of the base monad. It can be whatever you need. It doesn't have to be reliant on I/O, which means that like if you use identity as your base monad because you're doing a pure operation, then that's probably going to be significantly faster than if you were forced into I/O. And then if you do need I/O, you just put it in a fetch constraint. And obviously, the interpreters can use monad state as a constraint to manage their own state without those magic state keys from Haskell. So they can use a monad state to maintain whatever it is they need. I've got an example of that on the GitHub that shows how the state can be used. And in fact, actually, caching uses monad state this way, but I'll get to that. So then, if you need to do more than one data source in your application, we haven't really solved that yet, so we have to do something like this, where we have this union type, where a union is effectively just a nested either type that applies type constructors. It's a little weird, but essentially union of FGH is either FA or either GA or HA.
Is that the actual implementation?
No.
I was gonna say.
It's much more complicated than that. I jumped through a lot of hoops to make my decision on how that should be implemented. Sort of. So I did it first. Well, the freer monad with extensible effects, it's in the freer package on Hackage, used a union of a certain kind that satisfied this API, this kind. So I looked at that and I was like, that's really good, but let me take that, make a whole ton of changes to it, and use it as my own thing. And I posted that on my GitHub and had it as a submodule to the Fraxl repo, and then I just included it in and used that. And then someone comes along and says, hey, we accidentally did the same library, and says that his library does the same thing. And then I look at his library, and someone else posted on that, hey, accidentally the same library, and pointed to his library. But essentially, that last one, that last guy who made Vinil Plus has what I ended up using. And Vinil Plus, I don't know if you know what Vinil is, but Vinil is essentially an attempt at solving the records problem by using
vinyl. I mean,
vinyl,
vinyl.
It's fine.
That would make sense with the record problem.
Oh yeah, vinyl records.
Yeah. So vinyl, sorry.
Some people are
are easy puns or too much.
So the vinyl library offers this record type, which says given a list of record labels, we can give you essentially a nested tuple of these record labels. And then Vinyl Plus gives the opposite of that. It gave a co-record, and a co-record is just that if that was a tuple, the co-record is an ether.
Oh,
so
I see.
yeah. So co-record.
Is that what co means? Oh, I'm just kidding. Ever commit every single one of his libraries? Oh, this is a co-functor in the co-monad of what's up with co, man?
Yeah. So the co-record is essentially a nested either type like that, and then if you apply a certain thing to it, then it makes it into the union type that I was looking for. So that's what I settled on, was that implementation of the union type. And you can see the debacle of new types that go along into making union exist in Fraxl.
Wait, the debacle of what?
New types. There's union is a new type over functor correct, which is a new type over correct. Yeah. Anyways, where was I? Yeah, so this way we have one, if we take union and apply with it a list of data sources, then that gives us a type of kind star arrow star, which we can then apply to the free monad, right? And what that tells us is that we're going to have a free monad whose requests are any of the types FA, GA, HA, or whatever, right? So that gives us the option to use any of these types of requests at any time. So that gives us the ability to use multiple data sources at once. Yep.
How does it? doesn't know which one to pick. It's basically just which constructor it sees.
Yeah, basically. So when you submit a request using Fraxl, you'll say like data fetch my request, and then the union will take that and then say, okay, I'll shove this request into a union type, and then shove that union type into the free monad, and then that's the result.
I see.
So yeah, it's like shoving an A into either AB, shoving A into that by using the left constructor.
I see.
Yeah, so then we finally get this really nice type that we've been striving for the whole time, which is Fraxl R equals the free transformer over app over union R, which is to say Fraxl R is a monad transformer that operates on requests within R.
Wow.
Yeah. But this kind of leads to a problem, because the type signatures we've been using so far for computations in these free monads have been free over user DB over M over A, which leads to a problem. Like, how are you going to specify that with this, right? How are you going to say that, like, if I want a Fraxl monad that has my data source, even if it also has a bunch of other ones that I don't care about, which is kind of solved by the Vinyl Plus library with something nifty that somewhere is in here. There we go. So we have a class for monad Fraxl this way, where it simplifies everything. Where all you have to do is say monad Fraxl my data source M means that M is going to support my data source, and then we'll implement this function data fetch, which says given a request, actually produce a monadic value out of it, which is essentially lift free with union and app interjected in there.
Oh wow, F element of R. That's from the vinyl.
Yeah. So then in that monad Fraxl instance there, we have given a monad M, and F is in R, and that operator there comes from Vinyl Plus. Then we have monad Fraxl F on Fraxl R, which is annoyingly complex. But I mean, it results in really clean code, as you can see below. So like get users just says monad Fraxl user DB will return a list of integers. Get friends says monad Fraxl on the friends DB will return will given a friend given a user ID return the list of that user's friends. And then down here we see how they compose. We can say get users and friends where monad Fraxl friends DB and monad Fraxl user DB. And that says that this function, whatever calls this function, has to support both friends DB and user DB. And then you can see that because we support both of those, we can safely call get users and get friends.
They're relieved.
Yeah. And then I should have put the pragma, but I forgot to put the applicative do pragma, because that for loop technically would be applicative, which we don't really want. Well, I guess that's actually just identity, so that would actually be fine.
But you don't want it to be?
Either way, the point is that that should parallelize just fine.
Is Vinyl like a preprocessor, or is
No.
it just a library?
Vinyl's a library with some really advanced type system stuff.
Yeah, you can put Unicode symbols in.
Yeah,
in
so he
Haskell.
just made this operator that says like F is a member of R, which is really nice, but it led to needing undecidable instances, so it's complicated.
Okay.
All that means is undecidable. Oh yeah, okay.
Yeah, so
Because you can actually replace the for all with actually upside down A
oh yeah, I forgot about
with Unicode syntax extension.
that.
I'm very seriously considering doing that.
Yeah, so then with this get users and friends function, we see that like it can make use of two different data sources just fine, and those data source the functions that it calls don't need to also support both data sources. They can just support whichever single ones they
I
need.
see. So you get the MTL style.
Yeah, exactly.
Yeah.
And then
So Haskell doesn't have this.
Haskell doesn't have this. Haskell does not have a transformer. It doesn't have the type safety of knowing which data sources are used by a function. Yeah. So second to last major thing is caching, because I haven't talked about caching yet. That is a scary type. So I won't go in depth on it, but what matters is that gcompare constraint. Gcompare is from a library, I think it's from dependent sum library, and what it does is it says given a GADT F, you can use traditional ORD style methods on it to figure out if it's less than or greater than or whatever, regardless of differing type parameters, because since it's GADT, you can figure that stuff out. So you can essentially think of gcompare as a higher order ORD class. And that's the main part of that stack of constraints that matters. What matters after that is that we're taking an arbitrary fetch function for f and turning it into a fetch function over cached fetch of f, which means that when we run this fetch function, this resulting fetch function, it's going to have obviously different behavior. And the way it's going to work is it's going to substitute. It'll substitute your request handler with its own, and then manage figuring out when a request is duplicated or not.
Interesting.
And
so
then
this is like a drop-in replacement for your request.
Yeah, and in fact,
layer on top of it.
In fact, you can take any valid run Fraxl expression, which uses an ordinary fetch function, and then just say eval cached Fraxl instead of run Fraxl, and it works if f uses gcompare. Yeah.
That's awesome.
Yeah, so it kind of just works, which is really good. And the nice thing about it is that there's no need for implicit baked-in caching. If you don't want caching, you can get rid of it. If it's going to slow your stuff down and you don't actually need it, you can cut it out. Or if you're in a system where you do actually want to see the updates in the data, you can obviously not use cache. Or you can implement your own caching system. Like I said, this is just a substitution. So the caching fetch function is just a substitution on the other function, and so you can roll your own cached function that will that allows you to manage the cache on your own using whatever method you want. Like the default one uses mvar and a dependent map, or you could do however you want to.
Can you add caching to different sources, and some sources but not others?
You could do that. I don't have combinators built in to do that, but it wouldn't be too hard.
Because it looks like all you're doing is wrapping a fetch and building a new one.
Exactly. Yeah, that's the point. You're substituting an old one with a caching one.
So you would just run the normal run Fraxl, but your sources would you specify sources that are cached.
Yeah. So what you can do, I said you can use eval cache Fraxl. That's just a shorthand for saying, take my fetch, wrap it in a fetched cache, or in a fetch cached, and then call run Fraxl on that. It's a shorthand for that because that requires some kind of messy stuff. What was that?
But do you have map it over the union as well? Because you have
Yeah. So actually, union. That's what I was going to say next. The union says that if all of the members of the union are gcompare, then union is gcompare.
Oh, okay.
Yeah. So you can if you want to cache over all data sources, you essentially just provide your union fetch function there. Which, by the way, Fraxl comes with some combinators to take arbitrary fetches and combine them into a unionized fetch. So there are combinators to do that simply.
So even the union of fetches is a fetch.
Yeah. Union of fetches makes a new fetch of union, which you can. And then if they're all gcompare, then that fetch is gcompare, which means you can cache it.
Wow. That's super composable though.
Yeah, I know.
You could have cached caches.
Yeah, and yeah. So another example of just a nice little combinator that there's a simple async fetch combinator that says given f of a to I O a, it will produce a fetch F monad IO X. It'll produce an arbitrary fetch that can parallelize everything using the async library. Yeah. So you just perform your operation in IO, and then that combinator takes care of parallelizing them with the async library. Yeah, so I mean, you can see how like having access to this like fetch type that you can manipulate and move around, it makes for things being a lot more composable. Okay, and then the last little bit is testing. Yeah, so a problem with Fraxl, or Haskell, sorry, is that you can't interchange your interpreter. So if you want to test your data source, the only way you can do that is to have your data source class instance be specialized two different ways, where your state key tells you which way to operate, and then the implementation of the function chooses one of those and runs with it, right? Which is kind of a mess. It'd be better if you could just have two separate fetch functions like this. And in fact, you'll notice what's interesting about this is that the real fetch makes use of monad IO, but the test fetch doesn't have to be an IO. It's just using a state over a mock DB.
With completely different constraints.
Yeah, and so this is a pure version of Fraxl, right? You can take your existing IO-bound Fraxl code, and without changing any of it at all whatsoever, you can just run it with the test fetch interpreter, and then get a pure monad state-based mock of the database. So you can swap the interpreter, you can easily mock the databases, and you can test your impure IO code with a pure interpreter, making everything pure.
That's awesome.
Well, you're not testing your impure code with pure code. You're testing code that would normally be impure by making it pure. There we go. That's what I should say.
Right.
Yeah, so conclusion, free monads are great. Separating application code from interpreters makes things a lot more composable, and manipulating interpreters is a lot of fun and useful. I got like 4 resources of just some of the basic things involved. Like there's the David Menendez, that top link, he did the work on the free applicative that I'm using just because it's way faster than the standard free applicative. Then of course below that is the standard free package, which I'm not even using anymore. And then next is my blog about figuring out how to get applicative effects in free monads, and then last is the Haskell library.
Have you shown this to, I'm sure you've shown this to Simon, by the way.
I haven't reached out to Simon himself. What I have done is when I posted about applicative effects in free monads, I talked a little bit about Haskell on Facebook. I wasn't really talking about Fraxl or anything like that yet, but I was talking about Haskell just a tiny bit. And one of the guys who works on the Haskell team reached out to me and said, "Hey, you misspelled Facebook." So I got into a little bit of a conversation with him about Haskell and Fraxl and showed it to him, and he kind of helped me out with figuring out some of the performance issues. But I don't think it's gotten up the chain to like Katie Miller or Simon Marlowe or anyone.
I would not be surprised if they would actually just try to work it in, because so much the problems that you're solving are really important. For stability, for example.
Is there like a big performance difference in free key?
So yeah, performance. I don't have empirical numbers for you, so I can't like prove without a doubt to you that I know what I'm saying is true. But my preliminary tests would say that the overhead is 4 times worse on average when you're using IO as the base monad, and like twice better than that if you're using a pure monad as the base monad. Now, when you're working with something like this, you're usually doing IO-bound operations, which means that the overhead is not the main performance issue. So while the overhead is 4 times worse than Haskell's overhead, being within an order of magnitude is A, pretty good, and B, probably good enough for most people.
Because the overhead is coming from the fetches themselves.
Yeah.
Yeah, the overhead doesn't come, the overhead is probably not much compared to the actual I/O of going out and reaching the database.
So when you say it's 4 times, you're saying when you have I/Os that are just returning 3 or something.
If your actual fetch, the meat of your fetch function were nothing, if it were 0 speed or 0 time, then yeah, it would be 4 times slower on Fraxl than on Haskell.
That's not bad at all.
Yeah, no, it's not terrible.
I'm guessing with some inlining pragmas you could speed it up.
Probably, I'm not sure though. I haven't really experimented with that.
Yeah.
I know there was a problem where if your monadic binds were left associated, it would perform about 120 times slower.
Wow.
But I've managed to fix that. I used the reflection without remorse method to reassociate left binds to be right binds, which traditionally has some performance problems. But when we're already working with such an enormous amount of overhead, it's pretty unnoticeable.
Interesting.
Yeah, so the performance isn't bad. I'm happy with it so far, but I would like to get it better. I think the main bottleneck, I think, is just I think it's just the free monad is a little bit of a bottleneck, and that that's
sort of classic, right? Free monad is slow.
Yeah, and that's the problem that's what makes Haskell slow, is that it's a free monad. I think I could theoretically replace the cache with something that is faster. I could use a hash map with existential block fetch stuff, like the way that Haskell does it, which is kind of complicated, but I could do that and it'd probably be marginally faster. I could use
So that 4 times with caching.
Yeah. By the way, if you take out caching, it gets a little bit faster. So.
Yeah. That's because at that point the reason you have caching is because IO is your bottleneck.
Yeah.
Right.
And then let's see, what was next? The other thing I could probably try is currently the union that I'm using is this G80T that uses this weird recursive structure to go down the list of possibilities, and eventually you hit which one it actually is, which is significantly slower than if you used a typable approach, where you just said, here's the value, use typable to figure out whether or not it's the right type or not.
Interesting.
So typable could probably speed that up significantly, but honestly, in my testing, just removing union and just using single data sources, removing caching and just using non-cached data sources, the performance effect is pretty minimal with those. So despite that,
adding very little effect.
right? Yeah, and I'm talking about a data source that literally just returns a number. These things are pretty minimal. The caching. I can't remember the numbers that I had in my preliminary testing, but the caching didn't add much at all. The union hardly added anything at all.
Typically with your data sources, you're not going to have more than 5.
Yeah, and if you're using one data source, then you might as well get rid of the union because it's going to be marginally faster. But it's not noticeable really. It's not that big. The union's pretty fast. Yeah. So does anyone have any questions?
I just haven't thought on that.
I guess you got some example done.
Yeah, I can show you some of the stuff. I don't have it in slide form, but I can show you. Let's see. So I'll go ahead and, because I'm not using a proper screen recorder, I'll just stop my screen recording.